All right, welcome to the Explainer. Today we're going to put on our detective hats and dive headfirst into the beautiful chaos of high energy physics. We're here to figure out how scientists find these tiny, tiny clues in what is basically a data hurricane.
So let's just jump right in. How do you find one specific clue in a storm of a million distractions? Now, this isn't just some brain teaser, right? This is the question physicists at places like the LHC are wrestling with every single second. Think about it. They're looking for a needle in a haystack. A haystack they literally create themselves, and it's about the size of a universe.
Because you see, when you smash these tiny particles together at almost the speed of light, they don't just, break. Oh no. They unleash this insane explosion of new particles, mostly things called hadrons. It's a genuine storm of information, all erupting from one single microscopic point.
And I mean an overwhelming amount. We're talking millions upon millions of particles and data points just flooding the detectors in the blink of an eye. So our particle detectives have this monumental task of finding very specific, often incredibly rare clues buried deep inside all that noise. Okay, let's get our hands dirty with our first case file. The target? A very special particle called a prompt photon. Think of this as the smoking gun, a direct clue from that initial violent collision. It's a key piece of evidence, but there's a catch.
And this right here is the heart of the problem. The crime scene is absolutely flooded with imposters. We're looking for our primary photon, the real signal, but the place is crawling with secondary photons. They often come from the decay of other particles. And get this, they look identical to the real thing. It's the classic case of mistaken identity.
So how in the world do our detectives sort this out? It's not like they can interrogate each photon and check its alibi, right? So instead, they use this really clever technique that's based on, well, its social life, basically. It's a technique called isolation. And here's the key insight. Those primary photons are real clues. They're usually loners. They're produced all by themselves. But the imposters, they come from these messy particle decays, so they tend to hang out in a crowd, surrounded by other particle debris. So by simply demanding that our photon clue be found alone, we can filter out most of those false leads.
Pretty smart, huh?
Now, this is where it gets really interesting, because this shows that classic tug of war between the world of theory and the world of, reality. Theorists have this beautiful, smooth mathematical rule, the Frictionome criterion, that makes their calculations way simpler. But the experimentalists, they're working with actual physical detectors. They have to use a more down-to-earth method, like a fixed cone, and they have to deal with all the extra noise from other collisions happening at the same time. Two different tools, same goal.
Okay, so finding a lone photon, that's one thing. But now, let's level up. Let's tackle an even bigger challenge: how to sift through the main crowd. We're talking about that unruly mob of hadrons that makes up the vast majority of the debris from the collision.
So you've got quarks and gluons, the really fundamental particles from the initial smash-up. The thing is, they have this rule. They can't exist by themselves out in the open. So what do? They instantly transform into these huge directed sprays of other particles, and these sprays tend to clump together. Physicists have a name for these energetic clumps. They call them jets. And you can think of them like splatter patterns at a crime scene. Detectives need a really consistent way to identify and measure these jets to piece together exactly what happened in that first moment of impact. And this part is absolutely non-negotiable. If you want to compare what the theorists predict with what the experimentalists actually see, both sides have to be using the exact same rulebook for defining what a jet is. And that rulebook, that's what we call a jet algorithm. But here's the thing, not just any old rulebook will cut it. It has to be fair. It has to be robust. It has to give you a consistent answer, no matter how messy the event gets. And physicists have a special name for this must-have property. The rulebook has to be infrared safe. So let's put that back in our detective terms. Infrared safe just means your method for finding clues can't get thrown off by tiny, insignificant details. An infinitesimally soft particle, that's like a whisper in the background. A collinear one, that's like a particle casting a perfect shadow. A good, safe algorithm has to be smart enough to just ignore them. Let's make this super simple. Imagine your job is to count groups of friends leaving a stadium. That's your algorithm. Now, what happens if one person sneezes? A tiny, totally meaningless event. If that sneeze suddenly makes your rule merge two separate groups of friends into one,
Your count is now completely wrong. Your rule is flawed. It's unstable. It is not infrared safe. A safe algorithm, on the other hand, is way smarter. It sees the sneeze, recognizes it for what it is, totally insignificant, and it gives you the exact same count of groups as before. Your result is robust, it's reliable, it's the same every single time, and that is the gold standard we're aiming for.
Okay, so with that in mind, let's look at what seems like a really simple, really intuitive way to find jets, and watch how it can spectacularly fail this fundamental test of infrared safety. This is called the simple cone algorithm, and on the surface, it makes perfect sense, right? You find an energetic particle, you call it a seed, then you just draw a circle around it and add up everything inside. Simple, logical. What could possibly go wrong? Well, let's see. Imagine you have two energetic particles, and they're just a little bit further apart than the radius of the circle you're drawing. The algorithm finds two seeds, draws two circles, and correctly tells you, hey, we've got two jets here. So far, so good. Everything's working. But watch this. What happens if we add one tiny, low-energy, completely insignificant particle right in the middle of them? All of a sudden, that little particle can become a new seed. It forms its own cone, and that cone overlaps with both of the original big particles, sucking them into one single jet. The algorithm, which just a second ago said there were two jets, now says there's only one. It completely failed the test. And this kind of failure is an absolute disaster. It's not just a small error. As the quote says, it will invalidate the perturbative calculation. Let me translate that. It means the predictions from the theorists, the very foundation you use to interpret your data, become totally meaningless. Your whole investigation just falls apart. Your tools just aren't reliable. So our whole detective story, this journey into the chaos of particle collisions, has actually led us to a brand new mystery. We've learned that the simplest, most intuitive rules can be fooled really, really easily. And that leaves us with this final, fascinating question. What does a truly safe algorithm, a rulebook that's clever enough to never ever be tricked, what does that actually look like? Finding that answer is the key to the next big discovery. But, well, that's a story for another time.